Please, awesome.
Okay. So welcome everybody. So we have today a colloquium from Professor Daniel Verscharen, and I would like to first introduce you. And he studied in diploma in physics and astrophysics astronomy and graduated at University of Bonn in 2009. And since then he was then in the PhD in 2012, studying at the Max Planck Institute for Solar System Research and Technical University of Braunschweig, and his PhD advisor is Eckhard Marsch and Uwe Motschmann, and his thesis is on convected wave structure and spectral transfer in space plasma. And then he went to US, University of New Hampshire, as a research scientist and later research associate professor in his Space Science Center until 2017, and he went back to Europe. Or I don't know, is it Europe? So, but he went to University College London, Ernest Rutherford Fellowship at Mullard Space Science Laboratory, and then since 2022 he's an associate professor in space plasma physics at the Mullard MSSL, University College London. And today we will talk about electron-astrophysics, the multi-scale impact of kinetic electron physics in space and astrophysical plasmas. So, Daniel, it's your time.
Thank you very much. Then thank you for the kind invitation and for the invitation to be here. On the way this morning, I actually figured out the last time I was here was in 2012, exactly at the time, shortly after the PhD. So it's been a couple of years, and I'm very happy to be back and to talk about this topic. So when I got Rumi asked me to talk about electron astrophysics, and you may wonder, what does that actually mean? And so I hope I can motivate that a bit more. And I also have a picture here on the right-hand side. So this is the cover page of a white paper that we wrote for the Voyage 2050 initiative for the European Space Agency, exactly on this theme of electron astrophysics. And as the title suggests, right, the idea is that we look at electron plasma processes, ultimately, and think about what impact they have on the global evolution of these systems. And so I will slowly climb up the hill to larger and larger scales in this presentation. I want to start with some things in the solar system, look at some kinetic electron processes in the solar system, especially in the solar wind. It's kind of my own research area. And then go into these astrophysical topics, and at the end maybe present some mission concept ideas that we have motivated with this electron astrophysics theme. So there's a bit more astrophysics towards the end, and in between I will show also some theory. I will start with a bit of a theory perspective on the electron kinetics, but then also measurements from Parker Solar Probe and Solar Orbiter, of course, two really important missions for the study of electron physics in the solar wind. So I know that many of you work on different plasma environments, so I just want to introduce my plasma environment here, and that is the solar wind, as I said at the beginning. And these are some of the typical plasma parameters that we usually encounter at 1 astronomical unit. Of course, with these new missions, Solar Orbiter, Parker Solar Probe, we explore different regimes, different distances from the sun. But these are some typical values here. Flow speeds about 500 kilometers per second. Of course, you are familiar with the concepts of fast wind, slow wind, and eruptive events. Magnetic field strength, typically a few nanoteslas, right? So that's typically the interplanetary magnetic field. Also, that comes with a lot of variability. Temperature has cooled down a bit from the coronal temperature. We'll look into effects linking to the corona in a short moment. About 100,000 degrees, so down from about 1 million degrees or so in the corona. Proton density, just a few particles per cubic centimeter, so pretty empty, of course, but then space is big, so you have enough of material there. Plasma beta, so if you put these numbers together, you get a value that is of order unity. And of course, that is a bit of a problem if you want to work in certain mathematical limits, and the low beta limit, the high beta limit, and so on. So if you have about unity, that can cause problems. But the good thing is the solar wind actually gives us different environments, right? Through this natural variability, sometimes we have a plasma beta of just a few percent. Sometimes we have a plasma beta that is 50, 60, or even 100. And that's, of course, great if you want to use the plasma laboratory that gives you different conditions so that you can actually sample plasma under different parameters. And a very important number, and I think that's really what makes the plasma physics so interesting, is here the collisional mean-free path, because at 1 astronomical unit, the collision mean-free path is about 1 astronomical unit. So that means this system is basically not collisional, right? Collisions play a very secondary role, and we have to work with the methods of plasma physics, and we have to be careful with any fluid descriptions and things like that. I'll talk about this a bit more in a moment, because for the electrons, and as I said, I want to talk about electrons, that's a little bit different already. Collisions play a more important role for electrons, and also when you go closer to the sun, the environment is more collisional, and that causes interesting processes. But this is one thing that we always have to keep in mind, this collisionless nature of the solar wind. So I said at the beginning that we look at electron scales and how they impact global scale processes. So what are these scales that we actually talk about? There are two diagrams here. They are from this multi-scale review article that just introduce some of those characteristic plasma scales in the system that we're looking at. So the first one is about the length scales, and on the next slide, I will also have a similar diagram for the time scales involved in these problems. And we always have these bars here where the value here on the right-hand side in this cyan color indicates roughly averages that you would expect at about 1 astronomical unit. While the other end here, these are values somewhere in the mid to upper corona where the solar wind starts. Yeah, so that gives you an idea about the length scales. And here on the very big end, right, this here basically our system size. Of course, if you go to 1 AU, your system is kind of like the heliosphere up until this range. So it's really big, right? It's about 1 astronomical unit there. The next one, the mean free path, as I said, right, out here, they are roughly the same. And then it changes as we go closer into the corona. Then we have the inertial length for the protons over this range of scales, the gyro radii for the protons. And then we are already down here, right? You see the corona values. We're talking about the meter scale, or tens of meters or something like that. And then we get to the electron scales, right? Electron inertial length, electron gyro radius, centimeter range down there. And then finally, we have the Debye length here at the bottom. And one thing that you already see is when we talk about multi-scales and impact of scales on different evolutions, what we're looking at here is 12 orders of magnitude in scale, right? If we really wanted to capture the small scale electron kinetic physics and impact on the largest scales in the system that we have here, talking about 12 orders of magnitude, which of course you cannot simulate, for example, in a kinetic simulation. Right? Here for the time scales, the problem is even worse. So those are some of the characteristic time scales. We have the expansion time, collisional time, and then the times associated with plasma oscillations and gyration. And you see the same effect, right? This whole range of scales covers here 12 orders of magnitude. Okay, so what can we do about this? So I want to look at one example case where actually this mutual coupling of global and local effects, kinetic processes, and global expansion are important, and the solar wind is a very nice example for that. And I want to look a bit more into the electron populations in the solar wind. So this is a little view graph that illustrates what happens there. So we have the sun down here in the corner, and then we have the corona, kind of like this orangey range there. And that's ultimately, of course, the source that we have for our particles. And we make the assumptions now here and in the following discussion that actually in this environment, the material is quite collisional, right? And for the electrons, that's not a bad assumption down there close to the sun. And then if we go away from the sun, actually collisions are kind of like less important. We make a harsh assumption and say, well, there's one layer here, this distance R0. We say we turn the collisions suddenly off. Yeah. So of course, in reality, it's a smooth transition, but we'll just say there is one layer. We call that the exobase, and at that point, we turn collisions off. And above that point, what happens with the electrons? Well, they're basically just exposed to electromagnetic fields. They define what the electrons are doing. And in addition to waves and instabilities and so on that I will talk about in a moment, we have those global fields here with the electrostatic potential indicated in this blue shaded area here. and we have the magnetic field indicated in this pinkish color. And so now, if we look at the source surface down here, or this exobase surface, we have different families of electrons involved in this process, right? So we may have an electron here, this one, that is so fast that it can run against this potential, right? So for electrons, this is the decelerating potential, global ambipolar potential due to the pressure, ultimately the electron pressure. And so these electrons, they run against this hill, and they are so fast that they make it, right? They leave the heliosphere, and they form a population that we call the escaping electrons. But then some other electrons, like this one here, that are not fast enough, right? They run against this hill, and then they turn around through electrostatic reflection, and they come back to the sun. And when they reach our exobase again, they have the same speed, the same velocity even as when they started, right, in the simplified model. And then we have some particles, this one here, that are trapped, right? So those are particles that reflect at this point due to the electrostatic reflection, and at this point, they reflect due to the mirror force, because they run, when they go back towards the sun, they run into an increasing magnetic field, and the mirror force turns them around. And so this electron population actually bounces back and forth between those two reflection points. And if you measure now at a certain position R1, you always measure a combination of these different electron populations. And we'll look at that a bit more on the following slides, what that actually means and what you actually see. You already see that there's some electrons that you will never measure because they reflect further down. And you have potentially a very large fraction of these trapped electrons. Actually, at some distances, they are the dominant population in the electrons. And they make up altogether this electron distribution function. So now comes a little bit of a theory part, but it's not too heavy, because we want to find out how this electron population actually, or what this electron population actually looks like. And of course, as always, when we do kinetic physics, our starting point is a transport equation. It's a version of the Vlasov equation. And in this case, I've just kept it simple, just used one dimension. Some are steady state, so we have no time evolution. We say the system is already in this final state. And then the only forces that act on the particles are the electrostatic potential, right? This is the electric field term here as one acceleration. And this term here altogether, this is just the mirror force, right? So this is an energy conserving term that, depending on whether the field goes up or down, changes the pitch angle of the particles ultimately. And we say this equation describes the evolution of our velocity distribution function. And the nice thing is this is a very well-behaved equation, right? It's a first-order partial differential equation. And one way to solve this is with the method of characteristics. So you want to find the characteristic equations to this one. They are these two. And when you look at them a bit more closely, you see that they are basically forms of the equation of motion of the particle in the system. And then you can assume profiles for B as a function of R. For example, you say it just drops like 1 over R squared. And a function for how the electrostatic potential changes with R. You can, for example, link this directly back to the electron pressure gradient. And then you can solve these equations and use that to calculate what F is doing. And so the solutions for these equations of motion are these here. So you have this one here, which is just conservation of the magnetic moment, and this one is conservation of the energy. And what you can do then is you can say, if we want to know F, the actual complete distribution function at one point in equation R, you can always then express that as whatever your boundary condition is, F at a function at a position R0, where you put in the V perp 0, V parallel zeros from these two equations. Yeah? So this is a version of Liouville mapping where you can calculate the shape of F at any point based on a boundary condition. And now in the particular problem that we have, what is a good boundary condition? Well, a good boundary condition is the exobase, because we say at this point, the distribution is Maxwellian, so we have to, it's collisional and therefore Maxwellian, and so we can put in a lower boundary here and then calculate at any point in the heliosphere what the electron distribution function would look like. And so a starting point then as a lower boundary condition, you will see a few slides with similar diagrams coming on the next couple of slides. shows the distribution function f in color, right? So this is just color-coded the velocity distribution function. V perp is the perpendicular velocity to the magnetic field. V parallel is the parallel velocity to the magnetic field. And in this diagram, so everything that has a V parallel that is positive, those are electrons that move away from the sun. Yeah? And everything that has a V parallel that is negative, those are electrons that move towards the sun. And as we said, right, so below R0, everything is collisional. So that means everything with a positive V parallel is Maxwellian, right? So on this half here, you have a completely Maxwellian distribution just from the collisional soup of electrons in the corona. These electrons here, right, those that have a negative velocity, those are the electrons that were starting at the sun earlier, that get turned around by the electrostatic potential and that come back towards the sun, right? Those are the electrons that have a negative V parallel. And in their history, they were further away, and they're now coming back to the sun. And here, this line here, there's a sharp cutoff that you see in this distribution. So there are obviously electrons missing here, electrons that are not coming back towards the sun. And those are the escaping electrons that are not making it back, right? Those were electrons that started so fast at the sun that they made it through the potential and left the heliosphere. And they're not coming back, and that's why we have this sharp discontinuity here. The escape energy in the electrostatic potential. Okay, so if we take this as our initial condition, what we can do next is, well, we can say, okay, let's use our Liouville mapping technique that I have shown on the previous slide and apply that to this initial condition and expand that to a distance further away from the sun. If we do that, we end up immediately with this diagram. So this corner that we had at V parallel equal to 0 folds down, right? It folds down to this black line here. And these electrons, they are now a narrow beam in pitch angle. They have really folded into this narrow beam down there. This population in this corner between the red circle and the black line, those are the escaping electrons, right? Those are the ones that are not coming back to the sun. For traditional reasons, they are called the Strahl. Well, it's the German word for beam, but that's just from how they were discovered. Even in English, that's their name. These electrons that we have here, those are the ballistic electrons. So those are the electrons that get reflected and come back. And then we have a lot of empty space here, right? And this is space where, we just don't have any electrons that we detected at the corona burst, right? That we had in our initial condition. And if you remember from this diagram, right, I showed you that these trapped particles that are bouncing back and forth, well, they are never at the corona, right? They are trapped at higher altitudes. So that means, of course, we cannot find out what the distribution function looks like further out based on what we assume at the corona, because they're just never there. So where do they live? Well, those electrons, they would live here between the red circle and the black line. That's the region where you would have these trapped electrons. And since we cannot calculate them with our model based on the corona, we can make assumptions on what they do. And there are a few constraints on that, right? So for instance, we know that the total electron distribution has to have the same density as the total proton distribution, because otherwise we're not quasi-neutral. And we also know that overall, the flux of positive charges and negative charges has to be the same, because otherwise the sun will charge up. So we can kind of like patch together a distribution in this region and just put in some trapped electrons there. And our prediction would now be that, well, through these local processes, or through these global processes, these global fields, we would expect an electron distribution function that looks like that. And the really nice thing is now, of course, we can measure these distribution functions. And here are some measurements from Parker's Solar Probe, quite close to the sun, in the very same coordinate system where you see the parallel velocity here, perpendicular velocity here, and you see there's a really nice agreement between the predicted distribution. So we have this Strahl population here, the escaping particles, and then quite a sharp cutoff around the escape energy there, and the combination of all these different electron populations. So what happens next with this distribution, and I don't have enough time to talk through the details of these processes, is that, of course, a distribution like this or like this is not stable, right? This is not a Maxwellian equilibrium distribution. So they can drive kinetic instabilities, various families of kinetic instabilities. There is, for example, the strahl-driven instability of oblique Whistler waves that can be driven and they scatter these particles into this empty region here through pitch angle scattering. So we discussed this in a paper in 2019. And then once these particles make it into this regime, as soon as they cross the zero line, you end up with a deficit on this side, while here it's already filled up. And we often observe that. And there's a new instability that can take over of parallel Whistler waves that we have actually just described in big simulations that came out in January this year. So there are different local processes then that continue to process this distribution function further. The distribution function that is born out of these global effects. All right, there are some practical applications to all of this. You can imagine if you have a distribution function like that, it tells you something about how you are connected to the sources of the solar wind, right? Because those are particles, as we said, that are escaping. So you would always imagine that this part of the distribution, this strahl part of the distribution, always sits on the side that is anti-sunward, right? Because they come from the sun, so it cannot be on the sunward side. But because everything happens along the magnetic field, it will always be aligned with the magnetic field line. And so you can use that information to understand magnetic connectivity of the point where you measure the electrons. And that's something that has actually become really important in the context of solar orbiters, trying to understand magnetic connectivity. So I want to show you this little example here. This is from an article that we're writing for an ISI book, actually. So greetings to those at ISI who are listening at the moment. It's a book from it's an article in the book about electron kinetic physics, where we talk about electron transport in entangled fields and complicated field geometries. And so what you see here is if you have the sun here and you have complicated field geometries, if you launch the strahl always along the field, going away from the sun, then at different points, you would measure the strahl at different positions. So for example, here at point 1, you would always measure the strahl going in the same direction as the magnetic field. While if you cross over a photo sheet where the field line points back to the sun, here at point 2, you would always measure the strahl going in the opposite direction of the magnetic field. Or if you have a configuration like this one, where you have this snake in the magnetic field, if the strahl still goes along the field line, then you would, as you cross through the structure, always measure the strahl at the same pitch angle, right? Always at the same orientation with respect to the magnetic field. Or if you have something like this, right, then you measure situations where you measure bidirectional strahl going in both directions. And so we use this information now actually to link in situ observations with solar orbiter or Parker solar probe back to the magnetic sources and the sources of the solar wind on the sun. I have a nice example that's actually even older than Parker solar probe and solar orbiter. So it's this nice measurement here from ACE. And in the top panel, you see the pitch angle distribution of the electrons. So this is the angle. 0 degree means aligned with the magnetic field. 180 degrees means opposite to the magnetic field. And you see here the strahl population here. And then at this time, where the strong rotation in the magnetic field happens, suddenly the angle shifts, right? And so it goes from aligned with the field to anti-aligned with the field. And you see this is exactly this transition, right, from point 1 to point 2. Because suddenly the strahl connectivity has changed. If you had a situation where you have a rotation in the field, but the pitch angle stays, you would have situation 3 on the diagram. So we use this as a diagnostic tool to understand connectivity. Now I want to complicate this whole matter a little bit more, because the magnetic fields and the electrostatic potential and the whole system is not as nice and smooth as I showed at the beginning, right? With this blue shaded and pink shaded smooth potentials. But instead, of course, the whole system is really structured. And we have structures on many different scales. And our electrons encounter these structures as they whoosh around the heliosphere. And so here if we look at this electron here, electron E1, right, its gyro radius is really small compared to the size of these structures in the magnetic field lines that you see in blue. And then, of course, the electron basically just gyrates around its field line, follows that field line as it does. And that's okay, right? I mean, this evolution is still quite similar to the smooth one, even though the path length will be a bit longer for the electron as it goes along the field line. However, if you have an electron now, like electron E2, that has a larger gyro, either because it has a higher energy or because the structures that we're looking at are on smaller scales, well, this electron is not really magnetized here anymore and starts to diffuse across the field lines, right? So if you look at, for example, maybe some of you are working on energetic particle transport, this is really the process that creates cross-field diffusion in this case. Or if we have an electron like this one here, electron E3, that is an electron that moves into a region where the field strength is very low, and then the magnitude goes up again, so the electron can be reflected again, and it can form a trapped electron population also in local structures, right? The trapping doesn't have to happen on the global scales. It can also happen on local scales. And I want to show you now one example where this local trapping effect actually happens and is quite important in the solar wind. So this is work has not been published yet, but will hopefully be submitted soon by my PhD student, Jingting. And the idea was really what happens if you have an electron distribution that has a core and a strahl configuration due to the global expansion, if such an electron population runs into a magnetic hole. Yeah? So I know some of you are familiar with magnetic holes from the magnetospheric context, but we also see magnetic holes in the solar wind, where we have these distributions that then interact with these structures. So what you see are these are measurements now from solar orbiter, taken with the magnetometer here at the bottom and with our EAS detector that we built at MSSL at the top. And what you see here is in green, the magnitude of the magnetic field. The colors are the three components. And you see a very typical magnetic hole where we start with our field strength of about 5 nanotesla or so, right? And then here it drops almost to zero. Not quite monotonic, but still there are these fluctuations here. And then it returns. And the structure, they can occur on different scales. What we are interested in here are magnetic holes on ion scales or even bigger. So you can match this here, of course, with a convection time for the structure and think about the size of this. So this is an ion scale object. And at the top, we see the pitch angle distribution, same system as before, right? 0 degree means aligned with the magnetic field. 180 degrees means anti-aligned with the magnetic field. Here is our beam, right? This is the strahl population. And these red curves here, sorry, I know it's not so easy to see. We have to change that for the publication. But the red curve here, that indicates what is the trapping angle in this local structure. So all the particles between the red lines are particles that bounce back and forth between the trapping points of this magnetic field structure. And the particles outside, they are free particles that can move through that structure. What you see is here inside this whole structure where the field strength goes down, right, really down to the minimum. That's where this trapping angle becomes really wide, right? So most of the electrons in this region are in the trapped regime, and even goes to the point where the trapping angle eats into our strahl population, right, that we have from our global expansion. And so what Jingting did was she looked a bit more into what happens with an electron distribution if it encounters such a local ion scale or a bit larger than ion scale structure. And these are some cartoons that kind of like illustrate this point. So we have here the time series, right, an idealized time series magnitude of the magnetic field, how it drops down to the minimum at time t3, and then it comes up again. And what happens is you feed in a distribution that looks like this initially, right, outside the magnetic hole. And then as the field strength goes down, the trapping angle starts to widen up from the 90-degree angle here, right? So all the red particles, they are particles that are in this trapped region of velocity space. And the size of this wedge here at the top depends only on how far your magnetic field strength goes down. And all the particles here, because as long as they are magnetized, they conserve their moment. So all these particles, they reduce their V perp, while their V parallel magnitude goes up, right? So all these particles move in this direction, shown by these little arrows. And now if we push this further and we go to a smaller value of the magnetic field strength, then you see we reach a point where almost all the particles are in this trapped regime. Right? This is where the trapping angle on the plot was really almost at the maximum. Most of the particles are in the red region, and we are still pushing some of those magnetized particles down. And then if you go even further, you push it even more, the magnetic field strength goes even more down, then you may get a point where some of the electrons don't really feel this magnetic hole anymore, right? Because imagine you're an electron. If you're slow, you're gyrating, and you move slowly through this hole, everything is fine, right? Your magnetic moment is conserved as you do this, and you make it. If you're a fast electron, and you're gyrating while you run through this hole, well, you haven't seen the hole, right? And that happens to these electrons here under certain conditions. So, of course, you have to quantify that, really measure whether that can happen. But there is a point where if you push it down enough, where some of these electrons lose their magnetization in the structure, and they don't reduce the magnetic moment anymore. And what happens then, you see this here in the cartoon, right, is they remain where they are, and through this configuration, you start to create a little bump in the distribution function. And of course, what happens if you have a bump in the distribution function like that, you can drive new plasma instabilities, electrostatic plasma instabilities in the system. And so the prediction of this model was, when we go into a magnetic hole with this strahl configuration, and we push it all the way down, that then you trigger a new instability here, an electrostatic Langmuir wave instability. And with the RPW measurements on solar orbiter, we actually measure exactly the waves at the point where they should be. So these are RPW measurements, power spectral density as a function of frequency. This line here shows the predicted frequency of those resonant Langmuir waves at that point, and we see the enhancement compared to just the background before and after of the fluctuations exactly at that point. So this seems to really happen, right? And those particles, they scatter from the free region into the trapped regions. Some of those beam particles become trapped particles at that point, and the magnetic hole kind of like breathes out these Langmuir waves on very small scales, right? And so I think the nice thing about this process is it's one example where you see how this multi-scale coupling is really at work, right? So you have the large-scale global electrostatic field and magnetic field that creates a strahl core configuration. You have an ion-scale structure in your system, and on the smallest electron scales, you drive Langmuir waves in this interaction pattern. This is just one example that I wanted to motivate to show you how this electron kinetic physics actually happens in the system. A little side note, we have a project it's now coming to an end. There was a 2-year collaboration project funded by the Royal Society with the Italian CNR, where we talked with lab plasma physicists. And they had a really neat idea, and that was, can we reproduce these magnetic holes in the lab? And so this is a little lab experiment setup where they have a plasma vessel here. They put a filament on this side, and they inject an electron beam into the system. And so far, we have just checked out that it actually creates the Langmuir waves at the right frequency and so on. But what we do next is we take this magnetic coil and put that around this tube so that the electron beams start in the magnetized region and they travel into the unmagnetized region, kind of like going into the magnetic hole. And then we hope that a configuration that is stable first where it starts becomes unstable in the lower magnetic field. And that would be kind of like a lab representation of this configuration. I think that's quite interesting if you can think about lab representations of these astrophysical or space plasma processes. And that's a topic that we've been looking at for some time. It's not often easy because these lab experiments, of course, they have a very high level of collisions, right? So these systems are often dominated by collisions. The nice thing is it is possible to tune it so that, for example, the electron gyro frequency or the electron plasma frequency are still much higher than the collision frequency in these systems because the electron scales are so small. Right? It's possible to make it at least work for electron processes, and so we have a bit of hope that this works. All right. Now, as I promised at the beginning, I want to talk a bit more about the links to astrophysics and why we do this electron astrophysics theme. So this was an initiative that started with this white paper for Voyage 2050, but then also fed into this ISI effort that was this workshop last year where we're now writing the books, really thinking about the astrophysical implications of the work that we're doing. So I want to show you a couple of points here. Of course, one of the big arguments that we always use, and I think most of you know that also from writing proposals that you use that, that actually plasma is really important of all these physical systems, and especially that collisionless plasma processes can be really important. So here's a very nice image of an X-ray observation of a galaxy cluster. So we're really looking now at the biggest objects in the universe, right? So this is the intracluster medium. This is the gas that is between the galaxies in galaxy clusters. And that is a hot collisionless medium. And so sometimes you can observe this in these X-rays. And because the electrons are the most abundant species in these systems, right? Just from quasi-neutrality, you already need more electrons than any ion species, unless you have really only protons there. So they actually play a really key role. And one of the questions that we try to understand is really, how does electron heating work? We spoke about this a little bit this morning. Actually, heating through turbulence is one mechanism, but heat conduction in the form of heat flux is also a really important theme. And that relates, of course, to this whole strahl modulation question, because that is a way how you regulate heat flux in the electron distribution. And the key idea really in the electron astrophysics world is, well, how can we use measurements that we do in space, that we do in the solar wind, for example, or in the magnetosheath, or other environments where you can have in-situ measurements, to actually learn something about those plasma systems across the universe. And when we put together this white paper, we thought about some of the big key questions in plasma astrophysics that we can try to tackle with this approach. One question is actually, as I already mentioned, right, heat transport in the intracluster medium. So there are different competing theories explaining why the intracluster medium has the temperatures that we observe. So there's, for example, an AGN feedback mechanism where you supply energy to this medium through active galactic nuclei, or where actually heat conduction through electrons plays a role, where then, of course, these plasma processes that I described can really make a big difference on the heat transfer. And the other topic that came up in our conversations with the astrophysicist is actually the heating in accretion disks. And I should say, well, there are different families of accretion disks. There are these very high luminosity, optically thick, geometrically very thin accretion disks. They are very collisional, right? So in those systems, you would say, well, you can use some fluid concepts. You can think about heating in there in this framework. Well, it's a completely other family of accretion disks, including the one that we saw in these great event horizon images that are low luminosity accretion disks. So those are accretion disks where you have way less collisions in the system. They are puffed up donuts, really like geometrically thick, optically thin accretion disks. And in those systems, people expect very different temperatures between the protons and the electrons because there is no collisional coupling between them. And it's an open question in astrophysics is to understand, well, how is the energy actually partitioned between the ions and the electrons? And of course, that's a very nice system where we can think about turbulent dissipation, energy conversion, and energy transfer between the particle species that we may help answer through in-situ measurements. Just want to show this as an idea about how we can do that. as you saw at the beginning in my presentation, right, ultimately, all these kinetic processes, all these candidate processes that we have for heat flux regulation, for heating and energy partition, as long as they are kinetic, well, they lead to different signatures in the distribution functions, right? And so we kind of like combined a couple of ideas here, where you find, for example, if you have a lot of collisions, well, then you would end up with a distribution. If you have some resonant wave particle interactions cause these localized increases and decreases in the velocity distribution function. We thought about expansion processes that create anisotropies or these beam structures similar to the straw that I discussed at the beginning, right, that you see here in red. Local instabilities that then scatter the straw or these expansion features over into other ranges, or also other plasma processes like stochastic heating that would have their own signatures. And so the goal is always to measure those signatures in the velocity distribution function at the same time as you measure what happens in the electromagnetic field, because that's ultimately where this exchange happens. And so I want to present one mission idea that we put forward starting from this electron-astrophysics world, and that is the Dubai mission. This is the proposal that we put in for the first F-class call. The idea you see here, the tagline of the mission, right? Dubai, how the smallest scales in space control the biggest structures in the universe. That was kind of our tagline for this mission concept. The idea was really to make this a dedicated electron astrophysics mission. So our team consisted not just of the space physicists who know how to take those measurements, but actually also astrophysicists. We also had some lab plasma physicists involved because they are quite interested in some of these couplings of different electrostatic fluctuations with electromagnetic fluctuations that happen when you go to electron scales. So you see here, right, I mean, what you really need to measure for that is, of course, you want to measure those scales, right? You want to measure what happens on the electron inertial length, the electron gyre radius, and ideally on the Debye length scale as well. And then really think about how that couples to the global system and how these things interact. And so if you wanted to put together an electron astrophysics mission, what you really need is detailed measurements of the electron distribution, as I said, right? In a very high cadence, because you have to resolve things on the scale of a few hundred meters or so, right, as it gets convected over your spacecraft. And what you want is multi-point measurements, because you want to understand the type of electromagnetic fluctuations that are responsible for this energy exchange. And so those were the drivers for the Dubai mission. At the end, unfortunately, you know, Dubai is not flying. We lost against Comet Interceptor, so we were number 2 at the end in the selection. Comet Interceptor is number 1. Can't be quite upset about this because Comet Interceptor was also proposed by one of my colleagues, by Geraint Jones at MSSL, so we couldn't really be too sad about it. But, yeah, well, we keep trying with Dubai at least. We want to move forward with that. Okay, just go to this one. Want to mention one thing also because it happens this afternoon, so it's a little advertisement. If you're interested in these kinetic studies of space plasmas, especially in the solar wind, and also some of the topics about linking to what happens in the sun, I would just encourage all of you to become members of the Solar Orbiter Science working groups. So if you go to this website, you can sign up to the working groups. They meet every week. I mean, not every group meets every week. There are 4 different groups. There are some on reconnection, on turbulence, on connectivity science, exactly this important topic that I mentioned before. And you can just join Google Groups, become part of this community and discuss your science there. It's really open for everyone, so there's no restriction in terms of being from ESA member states or your career level or so. It doesn't matter. Everybody can join this. And actually this afternoon at 4 o'clock, we'll have our summary telecon. So after this talk, I have to go and run the summary telecon of the working groups at 4 o'clock. So if you want to join for that, you're very welcome to do that already. But this is something that is very important to me. We have now over 750 members of the working groups. So it's a really good community, and I think it works really well. With that, I want to close. Just want to summarize the key points that I talked about. So I think really going to these electron scales and not just looking at them in isolation as an interesting but isolated plasma process is really important. And I think when we think about new missions, new ideas for measurements, it's really worth considering this unexplored regime at those very small scales, but always having in mind how that couples to the large-scale structures. And I think I've shown you two examples actually where global processes, local processes act together, change what happens, really change the physics of the system, regulate what the evolution of the electrons, the heat flux in these systems does. And yeah, if we want to put mission ideas forward in this area, this is challenging because of those short scales and the required cadences that we need. But I think this is an opportunity to push the envelope and to think for the next generation of plasma missions. And with that, thank you very much.
Questions? Oh.
Thanks, Daniel, very much for the very interesting, very well prepared talk. I would have a question about the magnetic holes. These trapped electrons, obviously, very short scale, right? Or time scale. Did you or will you go for statistics where they occur? I mean, because I'm interested in large scale structures and whether these are in relation to large-scale structures, or are they at certain distances more abundant in comparison to outer? Because I'm having the Borowski spaghetti field in my mind. The field should relax, right, at a certain distance.
Absolutely.
Holes should then be less abundant. I mean, are you going forward in that direction?
I think that's a really interesting question, is the statistics of that. And actually, there is an earlier study led by the Swedish group from RPW that looked at magnetic holes and their relation to Langmuir waves, actually before we did this. So they kind of motivated this study. So they used a solar orbiter, and they have, well, it was from the first 2 years of the mission or so it's quite early times. But they looked at the statistics of magnetic holes, how often do they see them, and how often are they associated with Langmuir waves. And that was kind of like the motivation for us to think about under what conditions do they actually become Langmuir waves. So our prediction at this stage is to say they turn into Langmuir wave loud magnetic holes when the trapping angle really eats into the straw. That's the condition ultimately to create those Langmuir waves. And I think once this is worked out, then of course it would be really cool to go back to the statistics and to think about, okay, can we check that? Is that a robust prediction to say this is allowed, this is acquired magnetic hole? In terms of the radial distribution, or for example, association with different wind streams, I don't know. I think there's some work that people have done with cluster, when cluster was in the solar wind, to measure statistics of magnetic holes in the wind, but I'm not too familiar with that. It's apparently still, as you said, right, those objects, how long do they actually survive, and how easily do they form is also a bit of an open question, because actually even the formation process is not so clear, right? Are they steepened up mirror modes, or is there something else happening that creates them?
So some of, maybe first.
Okay. In your early slides, you showed these circling motion of electrons running towards the sun again. They are into a converging magnetic field. Is there any kind of loss cone or change in the distribution function?
Yes. So of course, I mean, this exospheric idea is quite similar to what is done in the exospheric models also for magnetospheric systems, right? And I think the loss cone in that sense is kind of it's a bit different, because we don't really lose the electrons permanently into the sun. We say we always have this Maxwellian source at the bottom that feeds these electrons into the system. But you're absolutely right that they run into this magnetic field that increases, and that turns them around through the mirror force. So in that sense, that's the same process as in the magnetosphere, for example, right? The effect on the distribution, I think, is the one that I've shown. So it's the one that creates these three distinct regions in velocity space, the escaping one, the ballistic one, and the trapped one. Yeah, I don't know if that answers the question.
It does.
Okay. But it's definitely a very related process to that, of course.
I just wanted to ask again about the role of the ion component, especially when you consider the solar wind.
Yes.
So we know this is expanding quasi-neutral medium.
Yes.
And you discuss only electrons.
Yes.
So they are partially independent due to collision loss, but not electrically disconnected because of the potential drops. So how these effects of the Coulomb interaction, what are the potential profiles?
Okay. Yeah, I've kind of given up on self-consistency a bit, right? Because I didn't talk about the proton. Yes, so I think one thing that I hadn't appreciated before I started doing this is really how different electrons and protons are, right? This big mass difference that we have make them almost behave in completely different ways. The protons, they march together, right? As one group, they move together from the sun into space, all with more or less the same speed. And that means it makes sense to define a parcel of plasma for the protons that you can move with, expand with, and you see how it changes as you go away from the sun. That concept doesn't make any sense for the electrons, right? The electrons are really subsonic. So that means they whoosh around in all directions, right? The electrons, they have this really, really wide distribution due to their large thermal speed. And the bulk flow or the bulk speed of the electrons is just a little shift on top of that. And what that means is that actually very different processes are important for the species. Now, for quasi-neutrality, as you said, and for the coupling of those two species, the only thing that really matters is what the bulk flow does and the density, right? So you have to make sure that the densities of the protons, of all the positive
functions should be consistent.
Exactly. And the distribution functions, they have to adjust to be consistent with that. But as I said, for the electrons, well, then we'll just shift it a bit like that, and it's consistent again, right? So it doesn't make a big difference. There is more to it, of course. There's a whole family of acceleration models for the solar wind that make use of this ambipolar field to actually accelerate the protons, because the potential that I've shown, the electrons, they run against the potential and decelerate. That means the ions, they get accelerated in this potential. And in exospheric solar wind models, that is the force that accelerates the solar wind, if I oversimplify that now. And it turns out probably for the base speed of the slowest solar wind, that seems to be fine. It doesn't really bring you to the high speeds that you sometimes observe of 800 or whatever kilometers per second. So you need additional energy deposition in the protons. But there is an effect due to the Coulomb interaction that you mentioned and the self-consistent field that pulls the protons out as it pulls the electrons back. But ultimately for charge neutrality and the current-free system, all you need is that the bulk flows and the fluxes, I should say, balance. That's all you need. And it's easy to do for the electrons.
So your solutions, which you show, they take this into account. So this potential profile self-consistently is included.
Yeah. Exactly.
So sorry, I'm not a plasma physicist. I have a question. You mentioned in your very well done introduction, by the way. Thank you very much. It was a great introduction to the field. That in this you have this. It's a coincidence that the proton mean-free path is of the order of 1 AU. Now imagine you have a T Tauri star, which is like more in X-rays, and it probably has also much higher wind loss rate. So that could be very different in other winds. So we always take for granted that the solar wind is that's what the stellar wind is. But if you consider these, could you, for example, have some? Well, maybe it's still like adiabatic cooling, and then the electrons get actually much less energy when they finally get free or so?
It's an excellent question. I think especially in T Tauri stars and other objects, radiation driving plays a very different role from the solar wind, right? So in that sense, I would already say they are quite different families of solar wind, because the radiation driving is really not relevant here, right? This is really through the electromagnetic interactions, and that would be different. But in terms of the adiabatic expansion, that's a really good point, because I mean, ultimately, you would expect for the protons, especially, right, as you go away from the sun and you expand into the void, basically, and the density goes down, the temperature would fall down with a, what is it, T to the R to the minus 4/3 or something like that, right? And that's not happening, right? The protons are hotter. So you need continuous supply of energy heating the protons to higher temperatures. For the electrons, it's actually a little bit easier because if you have a situation like the one that I've shown, and you have a skewness in your electron velocity distribution function, the skewness in the velocity distribution function means you have a high third velocity moment, and that means you have a high heat flux. And therefore, it's easy to supply energy through these fast, highly conducting, heat-conducting particles, and the electron temperatures, they don't have to drop so quickly. And that means there are some measurements, actually, most of them going back to the Helios time. There are a few early Parker Solar Probe measurements that measure how much energy deposition do you still need in the electrons. And it seems to be just a small fraction. So you can do a lot with the electron heat flux and the heat conduction in the particles themselves to supply that energy. For the protons, you definitely need additional heat to overcome the adiabatic expansion.
I have one question. Talk us about this changing solar orbit, the orbit coming up
Yes.
with higher latitude.
Yeah.
Do you expect some difference in terms of, the ambient to have more pollution or magnetic orientation gradients different temperature density, or?
So maybe once we had the latest Venus flyby for Solar Orbiter, and now the spacecraft is actually really tilting out of the plane of the ecliptic, and this will go even further in the coming years. And so we come into a very exciting phase for this mission now. Mostly, I would say, for the remote sensing instruments, because they can now observe the poles for the first time, but also from the in-situ perspective, maybe we have to wait a little bit longer, because at the moment, we are still too close to maximum. And then, of course, the magnetic field, the source regions are a total mess, so they can give you anything at any time, basically. Things calm down again, and we have a bit more of the, this nice Ulysses picture of the polar fast wind and the slow wind in the ecliptic. I think that is actually really exciting to measure those things close to the sun, because you have less twist in the field. The field is more radial, and so some of those features may be actually even clearer than what we've seen so far. So I think that will be really exciting, really interesting to do. But I think we still have to wait a couple of years for that. The other thing just to mention is on Christmas, Parker Solar Probe had its closest perihelion. They are now less than 10 solar radii or so from the sun. And so that means, of course, we have now really the closest measurements. I haven't seen the measurements yet because it's too early of those distribution functions close to the sun. And so in combination, I think it's actually a really, really good time to do more of that.
Any other questions, Owen? No? Okay, so no, nothing from that. Okay. Thank you very much. Then let's think of the speaker. Today, so, and we have, there's a solar orbit that everybody's joining, but in case if you're interested, we are still around.
Yes.
Yeah. So, and dinner, I think 6:30. Okay, thank you.
All right.